Hi, everybody. Welcome back to Dave's Math channel. This is another video in my new feature on daily math problems, which I've been posting on the Facebook group Classical Mathematics. Do this every few days. And the last one I posted involves something called Foucault pendulums. And here's a picture of the largest Foucault pendulum in the world. This one's in Paris, France. Yeah, and I forget how tall it is. I think it's something like over 100 feet. I know that. I've never been to the one in Paris, but I've seen several Foucault pendulums. There's one in Los Angeles near where I used to live at the Palomar Observatory. I think theirs is about 30 feet high. And I think I should explain a little bit about how these things work first. Um, um, well, maybe we should just begin. I'll get into that later. So anyway, maybe I should explain actually. What a Foucault pendulum is, in case you guys haven't seen one, this was, I think, invented around the 18th century by a French mathematician named Foucault. And what he discovered, if you have a really long pendulum, and it's free to, swing back and forth in any direction at once. You might think it keeps swinging back and forth in the same direction, but it doesn't. And the reason it doesn't is because the Earth is rotating. I mean, if you put this on the North Pole, it actually, the plane stays the same. The plane and oscillation stays the same, but we all know that the Earth is rotating about its axis. Therefore, from the frame of reference of the Earth, the pendulum looks like it's rotating in the opposite direction. And since the Earth rotates counterclockwise, as seen from the North Pole, then if you had a Foucault pendulum on the North Pole, it would look like it's rotating clockwise once every 24 hours. And if you put it somewhere besides the North Pole, it will rotate with a different frequency. I mean, if you put it on the equator, it wouldn't rotate at all because, the plane of oscillation isn't changing at the equator. If you put it at the South Pole, it would rotate the opposite direction, counterclockwise, because the Earth is really rotating clockwise from the point of view of the South Pole. And then in general, the rate of rotation depends on your latitude. Anyway, and the way it depends on latitude is well known. I'll get into that in a minute. So anyway, here's the problem statement. So the world's two longest Foucault pendulums are located. The longest one, like I mentioned, is located in Paris, France, and its latitude is 48 degrees 52 minutes north. And then the second largest one is in Boulder, Colorado. I've never actually been in that one. I've been to Boulder, but I didn't see the Foucault pendulum there. I guess it's at Colorado University, but I haven't been there yet. And its latitude is 40 degrees and 1 minute north, so it's a little bit further south than the one in Paris. And for that reason, they have different periods of oscillation. Turns out the closer you get to the equator, the slower they rotate. So the period of oscillation of the plane of the oscillation of the one in Boulder is slower than the one in Paris. So anyway, I actually posted a problem, another problem, easier problem pertaining to these Foucault pendulums about a month and a half ago. And in that problem, the what I asked was how often are the do the planes of oscillation both point in the same compass heading? Since they have different periods, that means their compass headings have to be changing with respect to time. I mean, if they agreed at one time, they wouldn't agree, a short time afterwards because they're rotating, the planes of oscillation rotating different rates. But, since they're going in a circle, they have to agree again after a certain amount of time. Just it has to the difference in the angle has to get up to 180 degrees, and once it does that, they're oscillating in the same direction again. Uh, we only care within 180 degrees because they go back and forth. That was actually a problem I answered, and I am going to answer that in this video But that was a problem. That was a previously posted problem. It's not part of this problem. So in that problem, in the previous problem, which I said I posted, I think it was August 11th, if I'm not mistaken. Um, I calculated the time interval, but where between the periods where they're oscillating on the same compass heading, and that turns out to be approximately 4 days, 12 hours, and 30 minutes. About every 4.5 days, both of these pendulums have the same compass heading in their oscillations. Um, but what I didn't ask in that problem is how much does that heading change? I mean, we don't expect it's going to be the same heading again once they agree again. And it turns out it's not. So a natural question to ask is what is the change in compass heading and in what direction? So that's part A. And then part B, I'm asking for, since the heading's changing, and presumably it's changing by an irrational multiple of 360 degrees, what that's going to mean, or 180 degrees, what that's going to mean is that at some time or other, both of their headings, both of their agreed headings, are both going to be within 1 degree of geographic north, or any interval, no matter how small geographic north. But for part B, I'm asking how often does it happen that they both are within 1 degree of geographic north, and they both their headings agree. Um, so that's part B. So that's what I'm asking for this problem. I guess it's a pretty complicated problem, but I'm going to go through the whole thing, including the problem I posted on August 11th. I'm going to do that first. This slide just kind of shows what I was saying earlier about Foucault pendulums. Their period of oscillation depends on their latitude. And I think this diagram kind of illustrates this in a nice way. Like I said, if you had a Foucault pendulum on the North Pole, it would oscillate with a period of 24 hours. And if it was at the equator, which is the picture on the right, it wouldn't rotate at all. But if you put it at some intermediate latitude, what you really care about is the sort of projection of the plane of oscillation. The direction of rotation of the Earth. Um, uh, uh, you know, with respect to the plane of oscillation of the pendulum. And that's going to be proportional to sine of phi, where phi is your latitude. So in general, the formula you get, I wrote it on Formula 1 on the bottom of this slide. Omega is the Greek letter we use for angular frequency. It's just the rate of rotation in radians per second, if you like. Um, or we could also put it in degrees per second, but which is what I do. So it's just the rotation rate. And the formula says omega phi is your latitude. It's equal to minus omega zero. Omega zero is the rotation rate of the Earth. And that's easy to calculate. That's just 360 degrees per sidereal day. A sidereal day isn't quite equal to an actual day. It's a little bit shorter. It's about 23 hours, 56 minutes, and 4 seconds. I'll explain why in a minute. But that gives you omega naught. It's really about 361 degrees per day, if you like. And then we have to multiply that by the sine of the latitude. That's going to give you the rotation rate at an arbitrary latitude phi. And the reason there's a minus sign here is because if you're in the North Pole, where the latitude is positive by convention, then the rotation is going to be clockwise. And mathematicians usually consider a clockwise rotation negative. That's a negative angular frequency. That's just a convention. Um, but anyway, so that's the formula for the rotation rate as a function of latitude. And like I said, omega naught is 360 degrees divided by T naught, where T naught is a sidereal day. And like I was saying earlier, sidereal day is a little bit less than an actual day. The reason for that is because an actual day, remember, a sidereal day is the period of time it takes for the Earth to rotate 360 degrees about its axis. But that's not the day we measure, because the day we measure is a little bit longer than that, because the Earth is also revolving around the sun, and it has to rotate about an additional degree to sort of catch up. We measure time by the sun, so what we call a day is really the amount of time it takes for the Earth to rotate about 361 degrees about its axis, because once it does that, the sun will be in the same position in the sky, approximately as it was the previous day. So anyway, so that's a sidereal day, and now we're multiplying by sine of phi to get omega phi. So we have a nice formula. 360 degrees divided by T0 is about 361 degrees per day, and we multiply that by sine phi. That's formula 3. And we can use this formula to calculate the rotation rate of the plane of oscillation for both of these two Foucault pendulums. For the one in Paris, turns out to be minus 271.9 degrees per day approximately. And for the one in Boulder, Colorado, turns out to be about minus 232.13 degrees per day. That should be negative. Both of those should have a minus sign. Anyway, so those are the rotation rates. And what we really care about is the difference. Because we want to know, for the problem I asked in August, I was asking, how long does it take before the rotation planes match up again? Well, the way you do that is you divide 180 degrees by the difference in the rates, because the difference in the rate is really the only thing that counts in terms of how the difference in the rates tells you how quickly the difference in the angle is changing, and the time it takes for the difference in the angle to change 180 degrees is just 180 degrees divided by the difference in the rates. I'm using absolute value here because the time has to be positive. And when you do the math, it turns out you get approximately 4.5263 days, or if you like more conventionally written, it would be 4 days, 12 hours, and 30 minutes. That's the time interval between times in which the compass headings of these two Foucault pendulums agree. So this was the answer to the problem I posted on August 11th, which I think one or two people actually solved, or at least they outlined the method for solving it. But now I'm asking for more than this. So for part A, I'm asking for how much the angle changes each time the headings match up. And to get that, what we really need to do here is we have to I'm calling T sub m the matching time. If we multiply that by either omega 1 or omega 2, omega 1 is the rotation rate of the plane of oscillation of the Foucault pendulum in Paris, and omega 2 is that of the one in Boulder City, or Boulder, Colorado. Um, and if we take the result modulo 180 degrees for either of these pendulums, we should get the same answer, because we defined it that way. So it doesn't matter which pendulum you use either of them. I decided to use the one in Paris, whose heading is changing 271.9 degrees per day. We multiply that by T sub m, which is 4.5263 days, and we get minus 1,230.70 degrees, but we take that result modulo 180 degrees, and when you do that, you get plus 29.3 degrees. And I'm using plus for the usual mathematical convention that a positive angle is counterclockwise. And so that means that every time the Foucault pendulum's headings agree, that heading changes 29.3 degrees approximately counterclockwise. That's what this formula is saying. So that's the answer to part A. What about part B? Well, there's kind of an easy way and a hard way to do part B. The easy way is we're asking, so we already figured out, the time interval between, the matching time when both headings agree, and we also calculated how much the heading changes. Forget about that part for now. Well, headings are going to agree at some kind of random angle. We don't know what angle they're going to agree at, but we're asking for when they both agree, and they're also both within 1 degree of geographic north. Well, there's a total of 180 possible degrees of headings. Remember, there's an ambiguity of a factor of 2 because the pendulums are oscillating back and forth. So we only care within 180 degrees the heading. So there's 180 degrees of possibilities and only 2 degrees of possibilities within 1 degree of geographic north. So if we just multiplied our answer for the previous problem by 180 over 2, which was 90, we should get the average time interval between when these two pendulums are both oscillating within at the same, the same heading, and both of those headings are within 1 degree of geographic north. And that turns out to be about 407.37 days, or more conventionally, 407 days, 9 hours. A little over a year. About a year and a month and a half. So you have to wait a while before they're both pointing north. But this is the average time. What's actually going on is a lot more complicated than this. They don't line up every 407 days. The actual behavior is a lot more complicated than that. And to actually do an analysis of how when they agree, when they're both within 1 degree of geographic north, you have to use continued fractions. I actually did this analysis. It's pretty complicated. I'm not going to go over my analysis, but suffice it to say, you can kind of simulate this with Mathematica, which I did. I wrote this Mathematica code to determine, exactly what times the two pendulums agree, their directions agree, and they're both within 1 degree of geographic north, assuming they both start pointing geographic north. You have to, put some initial condition in. So I made the initial condition. I assume that at some particular time, both of these pendulums, both these Foucault pendulums, are oscillating in the same heading, and those are both exactly geographic north. And then I wrote this code to see what will happen after a given period of time. You can put in, whatever time interval you want in years. I decided to have this thing run for 25 years. And I also put all the other relevant data in, namely T sub m, which is for about 4.52. Yeah, I think it was 4.5263 days. And I also put in the amount which the compass heading changes each time they agree, which was 29.3 degrees. So if you put in that data, what this code will tell you is it'll tell you all the times in which both of the compass headings agree, and they're both within 1 degree of geographic north. And it'll display the data in a nice format, which I'm not going to go over here. I'll go over it on the next slide. Anyway, here's the output. So the first thing you'll notice, this is a 25-year interval I ran this thing for, and there were 23 agreements within 25 years, not counting the first one, which is kind of put in by hand. And that's about what you expect, because remember I said the average time is about 407 days, a little over a year. So they're agreeing, roughly, not quite once a year, but close to once a year. But you should notice something else with this data. I think I just have to explain to you what all this data is in this table. The first column is just the index. It's just this just increases by 1 each time the compass headings agree, and they're both within 1 degree of geographic north. The second column is the number of it's just the number of periods, the number of multiples of T sub m since we started. And one thing you should notice here, these don't go up by two different size intervals. They either go up by 43, it turns out, or they jump. So there's like consecutive runs of 7 or 8 times in which um, it's 43 times t sub m. That's the time interval between agreements where they're both within 1 degree of geographic north. Most of the time, that is the interval between consecutive times. This happens 7 or 8 times in a row, it turns out. But then you get a big gap between those times. You get gaps of 381 times T sub m, which is about, I think that's almost 5 years. So the usual gap is only 194 days, it turns out, a little over 6 months. 6.5 months. That's about half the average. So most of the time, you only have to wait about half the average time before these two pendulums are both pointing the same direction and both within 1 degree of geographic north. But every 7 or 8 times that happens, you have to wait almost 5 years. So, but on the average, it'll be about 407 days. So that's how this thing behaves. Kind of a haphazard behavior, but that's what it does. That's when these two pendulums agree. I don't know. Be interesting to see if anybody decided to perform this experiment. Could probably do this pretty easily. Just have film crews at the Foucault Pendulum in Paris and the one in Boulder, Colorado, and we could determine times in which they're both pointing, oscillating the same direction and both within 1 degree of geographic north. We could actually observe this behavior if we wanted to. It might be an interesting experiment to perform. I don't think anybody's done anything like this, but it might be interesting. I was talking about this with my friend. I thought it might even be a good plot for a sci-fi movie. Maybe some aliens decide to visit Earth when both of these Foucault pendulums are both oscillating in the same plane and both approximately geographic north. I mean, you see sci-fi movies like this sometimes, so that wouldn't be a bad sci-fi plot, I think. But anyway, I don't know any other practical application of this. But I think it's kind of a neat problem. So anyway, that concludes my solution to this daily math problem. So thank you for watching. Long live math, and I'll see you guys next time.